predicting states of matter. It's it sounds odd, but you can't properly cook macaroni unless this is taken into account. I'm not talking about just liquid, solid, and gas. It's how one converts to another one, and when and where, and being able to predict how much energy is necessary just to boil water in the first place. Or sweating. Our body evolved this sweating process to cool ourselves down. Again, it's predicting states of matter. Ice skating, you couldn't even ice skate without states of matter and being able to predict and why one goes to the other and the funky things that are going on with water. Okay. So we'll hit on each one of those. Grace, what are they call them phases, but states also. What are the states of matter? Liquid, gas, and solid. Do they have different energies, Lewis? Yeah. In fact, which one has the lowest energy? Solid does. So if you go up the energy scale here, solid does, and then everybody, it's going to be liquid, and then gas or vapor has the highest energy. Jose, why? Yeah, oh, good one. Molecules are all nice and compact here. Liquid, less compact. Instead of the word compact, you could use the word what? Yeah. So instead of the static picture, think of the kinetic picture. Things moving around. Right? You're right. They're compact on solid, but they are moving in a solid. They are moving at the microscopic level. Not very much. Right? Liquid, things are moving around a little bit more. Gas, they're moving around a lot. There's all these different forms of energy. There's electrical energy. There's gravitational energy. What kind of energy are we talking about? These things moving around. Well, that's right. Heat energy. You apply this heat, and that's how you can get things to move faster. Right? That's the type of energy you're adding. The technical jargon in general physics class, I guess, just the K. Kinetic. Right? But you're right. You're adding heat to get these things to start moving faster. Right? That's the form of energy you're adding. Good. Okay. Predicting energy involved in an endothermic or exothermic phase transition. What the heck? These guys are endothermic or exothermic? So we have, in predicting the energy, we had solid, we had liquid, then we had gas. Now, solid going to liquid is technically called what? Melting. Liquid going to solid would be called freezing. And what this is saying, this whole idea is saying, is that's the same amount of energy. It's just in one, the energy was put in, the other one, the energy was kicked out. It's the exact same number. Liquid going to gas is called vaporization, or the B word, boiling. Gas going to liquid, condensation. Again, it's the same amount of energy. It's just that one's going to be positive, one's going to be negative. So let's think about this. If it's freezing, Jessica, if it's freezing, I should have wrote these down while we were talking about them. We had freezing, we had melting, we had boiling. Okay? Freezing. Endo or exo? Who done what? Just freezing is endothermic. We're going from solid to liquid. Well, freezing is going the other way, isn't it? Freezing is going from liquid to solid. So this is the only way I can remember this. Is I have to write SLG and then freezing, and I go, okay, well, I'm going here, I'm ending up down there. So am I going down the energy scale or up? I'm going down. So that means heat is being released. Heat's given off. So I'm going down the energy scale. I'm ending up at a lower state. So if I'm going down the energy scale, heat's given off. Freezing must be exothermic. Freezing must be exothermic. Melting must be endo, because I'm going up the energy scale. Boiling must be endo, right? How about, let's do this one. Sweating. How about sweating? Rebecca. Endo or exo? Going from what state to what state when you're sweating? Anybody help her? Going from... I don't know. I have to do it this way, otherwise my brain can't catch it. Going from what state to what state? Is it gas? So if you're sweating, that means you're getting wetter. If it's gas to liquid. Well, sweating, you're not covered in ice, though. Liquid to gas, right? Sweating is liquid to gas. You're just soaked in sweat, all right? And you're just like Obama there, you're just wiping off a towel and stuff, right? Liquid to gas. Everybody agree? So if it's liquid to gas, that's going to be endothermic. That means it's sucking up heat or it's releasing it. Endo means sucking it up. Doesn't that make sense? It's sucking up the heat from your skin. Yeah, cooling you down. Right? You're hot, you splash water on yourself, the water evaporates. So, sweating, right? Endo. Now, the reason why these are big deals is exothermic, you always put what sign on our answers? Endothermic, we always put what sign on our answers? Remember, which one was the negative? Exothermic was negative, right? You have a negative there, that means, hey, heat's being released. Positive sign is being absorbed, right? Okay. Positive, negative. Okay. So, we need little numbers here, right? How do you predict this amount of energy? Del H VAP. There's a different enthalpy, a different heat content for these guys. And if that's that one, VAP, delta H, FUS. So if you're going from liquid to gas or gas to liquid, you're supposed to use this enthalpy to predict these heat, these kilojoules. If you're going from solid to liquid or liquid to solid, you're supposed to use delta H. What's this VAP stand for? Vaporization. How about the VAP? Fusion, yeah. I don't think I've ever used that word, but fusion for melting or freezing. Okay. So if you're going to boil a bucket of water, or whatever the case is, you can calculate the amount of heat it's going to take to do it, right? Or if you have a bunch of water and it's going to condense, gas to liquid, you can calculate how much energy that water is going to release, right? You have a picnic, you have this soda can sitting there, it gets all this water around, it's all condensing, right? It's sucking heat, or is it releasing heat? This cold can sitting there, it's getting all this condensed condensation around it. If it's releasing heat, it's getting colder. It's absorbing a lot of heat, right? A lot, because that water's just sticking to it, and then it condenses. It gives off all that heat. It all goes into that can and makes the soda hot, right? Because you're going down the energy scale. Okay? Okay, so these numbers, like here's the enthalpy of vaporization. Would these numbers be different for different compounds? Or the enthalpy of fusion? Or they all have to be the same number? Valerie, what do you think? Yeah, different, right? Because just think of liquids. They're going to be stuck together more strongly or less strongly, depending on what the liquid is. Same with the solid. Same with the gas. They're going to stick together or not. They're different compounds. They have different chemical properties. So you have to look these guys up in tables. A lot of homework questions, they may not even give you the enthalpy of vaporization of water. They expect you to look it up. They just tell you that it's water. And they might say, how much heat is needed to boil 20 grams of water? That could just be the homework question right there. And you have to look up, oh, okay, I'm boiling, so I have to look up the delta H vap. And it's water, so I got to look it up in the table. Okay. You can get back into the mode of this. Sochi. Man, Chem 1401, this is pretty much what we did. We had one measurement, or one set of units, and then we had to do all these conversions and get it into another set of units. And that's this again. Where do you start? And where do you want to end up? "20 grams of water. That's where you're going to start or end up. That's where you're going to start. You want to end up with what units? Kilojoules. Now, the only way I think you can remember that is if you remember heat is energy, right? It's joules or kilojoules. I like to do this because then the rest is just finding conversion factors and then flipping stuff. Okay? To end up Daisy in kilojoules, what do we have to do first? Oh, she even has the right technical jargon. Molar mass, right? Molar mass, all right? And I think the big hint is, oh, this is what we want, but we need to get everything in moles first, right? So we're going to be using this conversion factor, but we got to get in moles first to use it. So she's right. Water is hydrogen, that's 18 grams in a mole. Grams on the bottom, otherwise they're not going to cancel. Remember doing that? Okay. Then, Erica, what would you do next? Convert the moles into kilojoules. Remember? This, I guess a hint to me is this unit always has to go down there. If you write that down there, and then sometimes it helps. It guides you. And then you recognize, oh, I just wrote half of this thing. So the 46 has to go on the top. Yeah, the 46 kilojoules. Divided by 18 times our 46. Get around 51. And since we're not worried about sig figs, just 2-3 digits are good enough. Okay.
So if we're not worried about sig figs?
We never are anymore, right? Okay. Phase diagram of water. The book expects you to know this, just be able to draw it. What are phase diagrams good for? Oh, it's going to be you pick a pressure and a temperature, and then you can tell whether it's going to be a solid, liquid, or gas. That's really all it is. Okay. But water is really special. Let's talk about why. All these phase diagrams have two axes. One is pressure. The other one is temperature. Right? Because that's the whole idea of it. Give me a pressure and a temperature, and I'll go on this graph, and I'll tell you whether it's a solid, liquid, or gas. So to draw all these phase diagrams, you just have to draw two lines. One is kind of this half parabola thing. Then the other one is a line, either goes forwards or backwards. Most every single compound is like that. You draw the line going forward, but not for water. I'm going to erase it. But this is what every single compound known to man looks like, essentially. It's phase diagram. Water is special. Water is going back. Water slope is in the opposite direction. Okay. And we'll I don't think life could exist on this planet without that line going back. A lot of people don't. Water is extremely special. Anyway, solid, liquid, and gas. If you have really low temps, all right, and you can crank up the pressure really, really high, this is probably which one? Solid, liquid, or gas? Crank up that pressure huge, really low temp. Oh, solid. That whole region in there is solid. You pick a pressure and a temperature and it lands in that region, it's solid. Crank up that temperature as hot as you want, it's going to be a gas, right? Because the liquid's going to boil on you. So that means this whole thing has to be gas. Well, I mean, the one in the middle must be liquid. Okay. So why is this a big deal? Seems to me the more I taught this class called physical science, and I learned several things in there. One is the astronomy part is extremely interesting. On this Earth, we have a huge-ass moon. It's way too big, statistically speaking, for our planet size. Why is that a big deal? Mars doesn't have it. Mars' pole, what's the big deal about the pole? The pole has to do with the rotational axis, right? It's spinning around some axis, and it's flopping around all over the place because there's no big-ass moon to stabilize it. That is a real problem if you want to evolve life. Because you need stable conditions over eons, right, to evolve life. You can't be having North Pole flopping from over here to over there, right? Poles flipping all over the place. That's a big problem. Here, we have a way too big for our planet. Stabilizes our orbit. The other thing is we're almost for water to... Okay, that's nice. But why water? What's so special about water? Because when it does get cold, ice what? Does ice float or does ice sink? Ice floats. Now, what if it didn't? Right? Ice floats, so you get... Where's it coldest? It's coldest on the bottom of that lake. So a little ice particle forms, and it floats up, and then you get ice freezing on top, and it's liquid on the bottom, so life can still exist. It didn't freeze solid. If it was the other way around, right, ice sunk, it doesn't matter how deep the lakes are, they're going to entirely freeze, because they're going to freeze from the bottom up.
I thought lakes, like, freeze from the top down, can fall through ice and hit water, which is ice, is still in water.
No. If you have a lake, and it's really, really cold outside, where is it the coldest? The coldest at the bottom. It really doesn't matter where it's the coldest, because little ice particles are going to be forming. And all that matters is where these little ice particles are going to go. Are they going to go up or are they going to go down? It just depends on their density, right? They go up because the solid form is less dense than the liquid form. They go up. So you get this, it could be 12 feet of ice. It doesn't matter. Just the thickness of the ice depends on whether you fall through it or not. You can drive trucks on this stuff. Up in Minnesota, they put in signposts. You can have pizza delivered out on Lake Superior. Because all these guys are out there ice fishing. What else is there to do? I'm from there, I know. Right? So that's how it is. But the reason why I'm harping on this is water is the only compound that does this. It's the only compound where you freeze it, the solid floats. Nothing else does. Again, so there's some funky, weird things going on for life to evolve on this planet. Every single other compound, no demand, that line isn't like this. It's like this. Okay? Now, it helps us to do some other things. This is one of them. You pull an ice cube, Lewis, out of the freezer. Is it rough or is it as smooth as silk? You feel it. Pull an ice cube out. I think it's rough, don't you? I mean, you feel it? It's rough. I'm not talking about holding your finger on there and melting the thing. I'm talking about feeling it. Ice is rough. Ice is very rough stuff. You can do the Zamboni thing if you want, but you don't have to. You can go ice skate out on a super rough lake. You don't need a Zamboni. And it's slick. I don't know if you ever ice skated, but it is really, really slick. It's very, very difficult. Right? Why is it so slick? You're on this very rough surface. Okay. What you have to think of is this blade is really wide or really thin. It's really thin. And you're standing on it. So that means if you rolled over someone's fingers, they're just going to slice them all off because there's a lot of pressure down there, right? A lot of pressure. I'm so surprised you don't hear that more often, people getting their fingers sliced. Anyway, it's really, really high pressure. So you look over here. I'm not on the ice skate. I'm just, it's just the ice. It's got to be, you have ice form. It's going to be really, really cold. So we're down in this region somewhere. Okay, and now let's just say the temperature's around here. Okay, so we go up on here, and, we didn't quite finish this story on here. If you have a temperature and a pressure that lands in this region, it's solid, gas, liquid. But what if you land on the line? What if the lines have? That means, all three would be right here, right? Solid, liquid, and gas are there. But if you're on this line, just solid and gas. If you're on this side, this line, just solid and liquid. So they're at equilibrium. So in other words, that's the freezing and the melting, right? You can actually figure out freezing and melting. And it's a really important one. You can figure out boiling points because this is where liquid and gas existed at equilibrium. So you pick a pressure. Okay, what is the boiling point? At this pressure. Well, all you do is go across, and you hit the line right at the equilibrium, and you go down. Well, that's the boiling point. Okay. What's the freezing point at this pressure? Well, you go on, you go down. That's the freezing point. Well, if you're ice skating, the pressure is really, really high or low. Right there under that ice skating blade. It's really, really high. So your pressure is way up here somewhere, right? Well, that means the freezing temp, you have to go across and down. Man, the freezing temp dropped like a rock, or did it go up? It dropped. I mean, it's way down to probably negative 350 degrees Celsius or something. If you want solid liquid at that extremely high pressure, you have to get it to negative 350 degrees Celsius. It's somewhere in that range. Well, no way is it that cold outside. So that means you have water under that ice skating blade. You are skating not on ice. You are skating on liquid water, an extremely thin layer of it. That's why it's so slick. And once you skate off of it, the rest is going to freeze again because the pressure is released. Okay, but that's water, right? Because water is the only compound that, this happened instead of the usual thing of that. Okay. Vapor pressure curve. So now the book wants to narrow in on, they call this the vapor pressure curve or the boiling curve, same thing. Okay? And I forgot to do a couple, before we move on, there are 2 points we're supposed to know the names of. Someone mentioned that one, where all three are at the same point. They call them points. This has a little TP. They call this the triple point. And what's that one? TC. The C stands for critical. So that's the triple point. And they call that the critical point. Critical. Or temperatures, right? Triple point temperature or critical point temperature. Okay. And they're going to be different for different compounds. But what's kind of interesting, I think, is something that they never tell you. And that's why this line doesn't go on forever. It ends. So you can't have equilibrium between liquid and gas once you get beyond a certain temperature. All that exists is gas. So you can't heat a liquid beyond its critical temp. And they never draw this in. But it's really a dashed line going up. Because if I go across that dashed line, now I'm higher than the critical temp. So liquids can't exist. So this is all gas. All right? It's all gas. That's why they call it a critical temperature. Water has a critical temperature. Once you hit a certain temperature, liquid water can't exist. It doesn't matter what the pressure is. It's just too dang hot. Things are moving around too fast. Okay. Vapor pressure curve. So we're going to talk about this boiling point curve, call it the vapor pressure curve. What is it and what is it good for? The question we're going to answer is really, why does it matter? But we have a container filled with water. Okay. How does the gas exert a pressure in the first place, right? If I seal it up. Crystal, do you remember, how did a gas exert a pressure in the first place? How did that work? Right? You have all these little molecules in there, so the gas is supposed to be there flying around, and they collide, right? So you have to have some container, right? And you have a pressure in a container because they're colliding with the walls of the container. And the harder they collide, or the more often, then the higher the pressure. Okay, and that's what, so vapor pressure is just the pressure due to the water. We kind of had vapor pressure of water last semester. We had to subtract it out from some questions, but so the vapor pressure of water is a pressure due to water up here that's colliding with the containers and things. So that's kind of what it is. Can vapor pressure be increased? Right? The pressure due to the water molecules up there, can it be increased? And if so, how? Oh, we could. That's a good one. We could stick more gas in there. But actually, that gas is going to turn into the liquid. The only way, if we stick more water vapor in there, it's just going to turn into the liquid. The reason why I know that is because there's only one way to increase the vapor pressure, to make more gas in the gas phase, because it's in equilibrium. So if you stick more gas in there, it just gets converted into the liquid. It's that Le Chatelier's principle thing. There's an equilibrium going on there. There's only one way to get more gas in the vapor phase, and that's to increase the temperature, add some heat, right? So you add some heat, now there's more molecules in the vapor phase. You increase the vapor pressure. What if we kept increasing the vapor pressure, right? Add more and more heat, right? Right? Keep on adding more and more heat. Later, that vapor pressure is going to be the same as, what do you call this? Atmospheric pressure, right? Which is like 50 or so. So once the vapor pressure reaches, there's nothing keeping it in anymore. Okay? Once they're the same, once the vapor pressure is the same as the external pressure. Okay? Folks at high altitudes, you really got to read the small print, but it's there. Who's at high altitudes? We're not. Who is? Yeah, Denver. Those guys who, well, don't get to go skiing this year, but, right? At high altitude, they have to read the special directions. There's special directions for people at high altitude. It says right there on the bottom. Why? The pressure for those guys, right, this external pressure, it's higher or lower than ours. It's lower because they're higher up. Yeah, that's all it is. Well, the higher up you are, there's less air above you, so there's less pressure. So the higher up you go, there's less pressure. That means their water is going to boil at a higher or lower temperature. Lower. You can use this to answer it even, right? Let's say we are, let's pick a point here. This is one atmosphere. This is San Antonio's barometric pressure. You go across, and you come down. Okay, that's where our water is going to boil, at this temperature. Okay. Well, you're in Denver. Okay, now the pressure's down here. Across, this is where their water boils. It's still hot, but not as hot. Either cook things long. But these guys aren't going to want to say, oh, you're at high altitude. You cook for 5 minutes instead of 10 minutes. No one's going to buy this. I got to cook this so dang long, right? So they try to come up with other things to fix it. Like they might have you add salt, and we can talk about that later. But this one just says increase water to 2 cups. And I don't know what good that's going to do. But maybe they're just making people feel better. But okay, so that's why you're in Denver. You got different cooking directions. Okay, let's see if we can check out some of these homework questions here. Let's look at the question first. They want us to predict whether this vapor condenses to a solid or a liquid when cooled. The vapor at some pressure condenses to solid liquid when it's cooled. So in other words, we have to draw the phase diagram of bromine. And that's what all that jargon is on top. So let's get started on that. Let's draw the phase diagram of bromine. So we have to have two axes. And remember, this guy was pressure, and the other one was temperature. Okay. And that guy goes like that. The other guy goes forward or backwards. He goes forwards, right? Now, you can put these little dots here. They're like dots on those two, for those 2 points. The book doesn't go through the whole long story I did about water's the only compound known to man that does this. So that's why they tell you this stuff. They tell you that the density of the solid is 3.4, the density of the liquid is 3.1. Which one is more dense, the solid or the liquid for this bromine? Which one's heavier? The solid is. The solid's more dense. So that means solid bromine sinks. Just like every compound known to man except water. So that's why this guy goes forward. That's why they're telling you this whole density story. But I kind of just disregard it unless it's water. Okay. Now we need some numbers in here. We need to have some idea of these numbers because they're asking us some questions. So triple point at negative 7.3 and 44 millimeters of mercury. Where do I put this negative 7.3? Jose, where do I put this negative 7.3? Yeah, right under that first dot. Go straight down. This is the triple point. That's its temperature. That's a negative 7.3. And, the pressure is 44. We'll go across. That's the 44. Okay, where am I here? Oh, the other one. 102. That's the critical point. So where do I put the 315? Yeah, find this guy and go straight down. Right? There's the 315. And the pressure was 102. So go straight across. 102. So I guess that's enough information to answer the rest of it. Let's find out. Bromine vapor. Oh, let's help ourselves out here. Where's solid, liquid, and gas? Solid goes... Jessica, where does the solid go? Yeah, this guy. She's pointing over here. This guy. Everybody, this one is liquid and gas. So let's put those in to help ourselves out here. Okay. Bromine vapor. Where am I supposed to be starting out here? Bromine vapor. Yeah, somewhere in the gas. We don't know where. Just your finger's supposed to be somewhere over here, right? Okay. At 40 okay, now they're narrowing it down. At 40 millimeters of mercury. So you're somewhere over here, but at 40. You can't be up here. You got to be pointing around somewhere down here, right? Okay. But it has to be below that dot, right? Because that's 44, so it's got to be down here somewhere. Who knows where? It's somewhere in here. Okay? It condenses to and cools sufficiently. So when I'm cooling, am I going this way or am I going that way? Yeah, because I'm cooling. I have to get colder into a solid. Or I'm just going to stay gas. But I guess they're saying condenses to, so actually something is happening. It's actually condensing, so solid, right? There's no way it can get to be a liquid because you're below the triple point. Okay. or it remains a gas. They said it condenses. Bromine vapor. So again, we're a vapor, like Kathleen said. You're over here somewhere. But now we're at 400 millimeters of mercury. So where's 400? Way the heck up here somewhere, right? I don't know, right? 400, because this is 102, so 400's got to be way the heck up here. Yeah, Sochi? Oh, they changed units on us? Oh, they did. I never even noticed that. Oh, shoot. Okay, so how many millimeters of mercury is 102 atmospheres? I'm going to screw up. Let's just so remember how to convert, but let's just change it to millimeters of mercury. There's advantages to all right. Otherwise we got to convert, and it's not going to really change anything. And remember, I have to give you all these conversions. There's 760 millimeters of mercury in 1 atmosphere. So you have to convert it. But that's just okay. So we're up here somewhere, and we want to cool sufficiently. So again, we're going to go to the left or right. This one, go to the left. Okay. So we're going to turn it into a liquid. You get it even colder, you're going to turn it into a solid. Yeah. But at first, it's a liquid. So, whoop. Okay. Yeah. Well, it says condenses to liquid. You could argue either one. I think you're right. All right, because you're up here. You got to, Amanda, think of find 400. You got to be a vapor. Like remember, Kathleen said you got to be in here somewhere to start out. But it says 400, so you got it 400 millimeters. So now you're more specific. Now you're up in this region. Who knows where? But you're somewhere over here. And you got to get colder. So where are you going to hit? You're going to hit a liquid first. And then you're going to hit solid. Yeah. I think it should say condenses to what first? It would be a better answer, better question, right? Condenses to a, okay. But isopropyl alcohol, you've probably used that stuff before to disinfect, right? Your skin gets cold, evaporating. How much heat is absorbed if you dumped on 2.25 grams? Rebecca, where do we start out on something like this? Yeah, it's going to be a converting problem. You want to end up in what units as your final answer? Anybody? Kilojoules. Now, realize in these questions, in these converting questions, you can really start anywhere, I think. But like, if you want to start with the 42.1, that's fine. But you don't know whether you should write it as 42.1 kilojoules on top or 42.1 kilojoules on the bottom, right? So that's why I think it's always safest to start with that 2.25 grams. Start with the amount, the measurement. Okay. Let's do that. CH3, CHOH, CH3. Okay. What's the technical jargon for what we're doing first, Valerie? What's the technical word for what we're going to do first here? We're going to find the molecular weight, molar mass, right? Okay. We need, she's right. Like 3 carbons, 3, 4, 5, 8 hydrogens, and an oxygen. Hopefully someone will get that. 180, that sounds huge. This carbon is 36. 60? Oh, a couple folks got 60, so I think we can trust them. 3 got 60. That's good. Okay. Last step. Sochi, where do you put the 42? On the top. All right, because then everything should work out. Okay. Let's make a little dot for that A so it's more clear. Okay. This shown here is a phase diagram for some compound they call Z. The triple point is negative 5.1 at 3.3. The critical point is 51 at 99.1. Okay. What's the state of Z at A? Daisy, what's the state at that A? She's gas. Everybody agree? Yeah, remember you have solid, liquid, gas. Okay. AS, I guess. If we increase the temperature from the compound at position A to 60, we got to put in some numbers, right? Let's put in these numbers for the triple point. Triple point is negative 5.1. 3.3 atmospheres. Critical is 51 and 99.1. Right? Make sense? Otherwise, I don't know where 60 is, I think. So we are going to increase the temperature. Should be of the compound at position A to 60. So we're going to go to 60. We're going to end up being what? Gas. Give me a gas. How about this next one, Erica? What is the state at 20 degrees Celsius and 65 atmospheres? Liquid. Looks like, right? It's got to be somewhere. Right? The 20 is somewhere around here, and the 65 is somewhere. I think she's right. Do you see it that way? Would it be possible to make the compound, starting under the conditions of part C, a solid by increasing just the pressure? So we want to know if we can start at C. So C, we said, was somewhere up here somewhere. I don't know. Just take an X there. It's somewhere around there. Right? That's where we were at. If you increase just the pressure, can you make it a solid? Increase just the pressure, Grace. Can you make it solid? No, right? You agree? Because all you're going to do is just go straight up. So let's stay a liquid. Okay. We're supposed to use that figure, Lewis, to get the boiling point of diethyl ether when the external pressure is 350. Now, what is this figure? We have vapor pressure, and then we have temperature. So these are those boiling point curves, or the vapor pressure curves. This is only part of the phase diagram. It's just that one arm. Lewis, what would be the boiling point if the external pressure is 350 for diethyl ether? What would you guess? Yeah, somewhere around here, around 15, 18. Because what he did, he's right. He started around here. He went down. It's got to be somewhere. No, 15. I think he's right. Like 18 sounds like a good number. Somewhere around there, 15, 18 degrees Celsius. How about for carbon tetrachloride, Jose? And the external pressure is 250. The external pressure is 250 millimeters of mercury. What's the boiling point of carbon tetrachloride? He says around 40. So 250, get the carbon tetrachloride line. Yeah, right? Around 40. Okay. Oh, that was it. Not so bad. So come by if you have. There's no lab this week. So come by if you have some questions. I'll be glad to help you out.